Okay, so hi everyone, I'm Luciano, and this talk was titled Posterior Predictive Sampling in PyMC free. And I'll talk about some recipes to do posterior predictive sampling and avoid all of the shape problems, or most of the shape problems that can underlie the predictions on new data sets. So first of all, I'll do a really basic background of what's posterior predictive sampling and when do we use it. So the common workflow for PyMC free is that first, you collect data that, they can come from many sources, and you have to think of a way in which this data is generated. Thinking of a way in which this data is generated leads you to writing this down in a systematic way in the PyMC free model instance. So you have to write down all of the prior distributions for unobserved parameters, and also how these condition the observations. Then, once you have that written down, you do inference to learn things from the unknown parameters or the unobserved parameters. And you can either do this with Monte Carlo, Markov chain Monte Carlo, variational inference, sequential Monte Carlo, or one of the many tools that come in the package. Then you check the convergence diagnostics for the inference results to see if everything makes sense, or if what you've learned is something that you could trust and is unbiased. And then finally, the final point is that you try to see if the model and everything that you learned from it actually make predictions that do make sense. And how do we do that? We do that with something called the posterior predictive distribution. And this distribution is, in essence, the probability of observing new values conditioned on all of the data that we've seen so far. So basically, during this entire presentation, I won't try to go into any math. So I'll try to explain with my words what all of these distributions are, and just write down the most simple stuff of math that I can think of. So the probability of new values conditioned on everything that we've seen so far. The things that we've seen so far basically determine the posterior that we've learned from the unobserved parameters. So given the trace of our sampled parameters from the posterior distribution, what do these tell us of how the new values should be distributed, or the new observations should be distributed? Usually this distribution has no analytically closed form. I'm talking about the posterior predictive. And so PyMC provides a function called sample posterior predictive, and also its fast variant, that is able to draw samples from this distribution without having to calculate an analytically closed form for it. So this presentation will be about talking about the cases in which both the sample posterior predictive and the fast variant fail systematically. And we'll try to answer 3 questions. When do these 2 functions fail? Why do they fail? And how can we make these work? So to start out, we'll talk about the model in which everything works out fine. So it will be a really simple model, and then throughout the presentation we'll start including a bit of a more complicated variant of the same model that will start to show the problems that you can typically encounter with posterior predictive sampling. So we'll start out with a linear regression where we have the slope that's unobserved. So we define a prior over it. It's a normal distribution. We have the intercept that's also unobserved, and we define the prior as a normal. These 2 combined with the regressors x define mu, which is the expected value for our observations, and then we finally assume that what we observe follows a normal distribution that's centered around this mu vector. And just to make things simple, we will assume that we know the true variance of the process, which we assume is 1. So given this generative process, we can create some training and test data that actually follow the process. So I won't go into any details. All of the presentation will be available on my GitHub account. So you can go and slide through all of the Jupyter Notebook source code and some intermediate results of convergence that I don't actually show here. So the important stuff is that we'll assume that the true slope is 1, the true intercept is 5, and we'll be defining the regressors x for the training dataset, and then the regressors x for the test dataset, and these 2 will have different shapes. So we'll have a bigger training set and a smaller test set. And we'll see if we can actually make predictions on these differently shaped datasets. So when we try to define this model, this generative process from the math into PyMC3, we have to use all of the constructs that PyMC3 gives us. So we have the model instance, where we define the named coordinates, and this is the context manager. So we define also the regressors, which we use the PyMC data instance to encapsulate the vectors of the training data. This allows us to then change the data for the regressors when we do predictions in a way that's quite easy. And then we define the two unobserved free random variables that will be the slope and the intercept as normally distributed random variables. We compute the mean for the expected output, and then we wrap the actually observed output in a PyM data instance, so it's easy for us to change the values once we do posterior predictive checks. And then we can also, once we define all of the model, we can sample from the prior predictive distribution. We can sample from, we do inference to infer the posterior distribution on the slope and the intercept. And we can also sample from the posterior predictive for this situation in which we're doing samples from the training set. So usually sampling from the same training set, doing posterior predictive samples, will always work or should always work. And we'll go into situations in which once we change we go outside of the training dataset, things might break. So the model looks like this once we plot it as a graph, like the generative process as in the graph visualization. We have the two random variables, the two free random variables here separated. Both of these are scalars, and they both control the observed value, the observed random variable, and it is also influenced by Vx regressor data. And the observations have a shape 21. And you should remember this shape because we always use the training set to have 21 elements and the test set to have 10 elements. So when we try to plot the predictions of our the samples from the posterior predictive, they will look like something like this. So basically what we see is that in blue we have the actually observed training data, and in black we have samples from the posterior predictive distribution. And we can also use RVs to plot the confidence intervals, or use all of the tooling that RVs provides to have different visualizations. In this case I just want to plot some of the actual samples that were drawn from the posterior predictive. So now let's make some predictions of the new data. So the other difficulty, as I said before, will be that the new data will have a different shape than the training data. So how do we change the values between the train and the test data? What we recommend always is to use the PyMC3 set data function that grabs the value or the names of the data containers that were X and Y in this case, and we set the values to the test set in these two variables. And then we draw samples, in this case using the fast posterior predictive function, and we can plot the distribution or the samples that we've drawn from this distribution, and also overlay the actual observations. And we see that everything worked out fine and there were no errors, but something isn't right. So once we try to plot the model graph here, we'll see something that actually doesn't cause any problems, but it's a bad omen of things to come. Because you can see here that we have the two scalar random variables, intercept and slope, everything fine. We have the observed that's shaped like 10, that's fine because the test set has 10 elements. But what happened with our data containers, X and Y? They seem to have a shape that hasn't changed. They seem to have a shape 21. So something seems to be off in this situation, because we would expect both X and Y to have the same shape as the test data. But In this case, this isn't really a problem for us because the shape for the plotting comes from a parameter that's statically given once we construct the elements, and the actual shape that is used both for posterior predictive sampling and for sampling is the thing that's defined on runtime by the set data value, the set data function from PyMC3. But for plotting, there's for some reason still the wrong number. But this is something that, some sort of a bad omen. So we can see that something in the shape gets defined statically, and sometimes this static shape will actually bring in some problems for us for the posterior predictive samples. And all of this have to do with shape problems, which are present almost throughout the entire package. So we have made a lot of efforts for reducing the impact of shape problems. Most of the inference does work perfectly, like nuts, all of the posterior samples, sequential Monte Carlo. But once you try to draw samples from the prior or draw samples from the posterior predictive, there are some things that can actually go all right. So shape problems can creep in from anywhere. So what's the actual problem? Why do shape problems come up in PyMC3? In our case, the thing is that we're mixing Theano tensors that are the random variable values with distributions that are not Theano elements at all. So our distributions are not Theano tensors, they're not Theano operators, and they do a mix of things to try to grab most of the best of the world of Theano, but there's something that they can't do. They can't infer the shape implied by symbolic parameters, because remember that Theano tensors are symbolic entities, and sometimes their shape is undefined once you provide them at build time, and they only become defined once you do the runtime, once you compile all of the computational graph of Theano into a function and then call it, giving some values for the input. So the distribution shape sometimes is completely detached from any change that you can perform using the set data from PyMC3. And things can get very messy very soon. So we'll basically do a really simple extension of our linear regression. What we'll do is we'll have in a label that's a latent label that we don't observe, and we have two linear functions that the data can come from. So for each of the individual regressors x, each of the values, each of these will come from a different one of these two linear functions that have different slopes, and the label that represents which of these two functions the regressor comes from, and also the observation in the end comes from, will be unknown, and we'll have to infer it from the data. So here what we're basically saying is that the label comes from a categorical distribution, and we have to change the way in which we generate the data for this process. And we just basically say, okay, there's two functions, two linear functions. One will come out 30% of the time, the other will come out 70% of the time. And the functions will have slope 1, that will come 30% of the time, and slope 3, that will come out 70% of the time. And they both share exactly the same true intercept. So none of these things are actually known for the model, that they don't know the true slopes, they don't know the true intercepts, and they won't know the label from which of each of the data points comes from. So we now generate the training and the test set using this new generative process, which you can look at with care online in the notebook. And when you try to define the generative process using our PyMC3 model instance, you just have to add in some new coordinate component that's for the mixture component, mixture. So now we have two labels, and we'll call these either belonging to one or the other functions a component, the component to which the regressor belongs to. And this would be the component dimension. And so now we basically have exactly the same model as our linear regressor, We have the regressor encapsulated in data, but now we've added the label that comes from a categorical distribution. And the key thing is that we're not trying to learn the probabilities for each of the labels. They will be fixed and frozen to the true ones that are 30 and 70%. And then this long line here that seems strange is the definition of the slope. So basically we're saying the slope comes from a normal distribution with 0 mean, 10 standard deviation, has the dimension that follows the component name that has 2 elements, and then we add in some transformation and also a test value to ensure that we don't have any label switching, because for those of you that do know, this model is something called a mixture or a Gaussian mixture model sometimes, or a linear mixture model. In this linear mixture model, you could infer the slope for each of the components, and they could mix up and switch the label. So with this order transformation, and you should look that up somewhere else, I won't go into the details, with the order transform you will prevent the label switching for the slope. So this is the long line, but you really shouldn't care about that. That won't have anything important or any impact at all for our talk here. So once you have the model defined, you can draw samples from its prior, you can infer from the posterior distribution for the unobserved parameters. Remember that the label is now a discrete value, and it has a discrete random variable, and so you can't use actually only nuts. You can't use Hamiltonian Monte Carlo. You have to do nuts within a Gibbs sampler or Metropolis Hastings for the discrete one. So be very aware that you could have biased results and your inference could be wrong. So you have to take a lot of care with the diagnostic checks, which I won't do at all here, because we're focusing on making predictions for the posterior predictive and seeing when things can go wrong. So we'll just assume that everything went fine with the inference, and we try to sample from the training dataset, the posterior predictive. And things go well with that for the training dataset. And we can also see the the model's graph representation, where you see that things are mostly the same as before, but now we've added the label categorical distribution that goes into the observed random variable. And our predictions on the training set do work, and they don't error out. But what happens when we add in the test data? And remember, the test data now has a different shape. So what happens is that we start getting value errors, where some things like, in this case, say, input dimension mismatch. We have something that has a shape 21 against something that has shape 10. And remember, the training dataset had shape 21, and the test dataset had shape 10. So what this is actually pointing out is that something that was defined at build time based on the trained dataset was not changed when you did the set data, and is being multiplied against something that did change with the set data. So we're having something that's mixing up, and you get this wrong behavior. So we can ask ourselves why. So once you do the plot, we can see again all of the problems, that the observed distribution has the shape of the test values. We did know that these two data containers were wrongly labeled for the graph with representation, but now we also see that the label categorical distribution has shape 21. And this is a really important thing, because it means that the categorical distribution shape isn't being changed by the set data. What happens, so this means that label could be a conflicting parameter for us. So we could try to represent the model in a different way. We could try to marginalize the label out. So we remove the need of having this discrete random variable. And how do we do that? We do that with the normal mixture distribution. So we have exactly the same slope, the same intercept as before, but now we have a mixture of several normal distributions with different expected mean values that are depending on the regressors and the slopes of the functions. And then all of these mix up with the mixture distribution, the normal mixture distribution. So how do you define that using PyMC3? It's almost exactly the same as before. We have the regressors the same, the slope the same as before, the intercept the same, mu the same, but now we're doing a multiplication of the slope by the regressor for every different possible value of the slope for each of the components. And then we're passing that all into the mixture distribution. And the key thing here is this line here, where we're defining the component, the components distribution shape. So we're saying that we'll have this length of the components as the last element, so we'll have two components in the mixture, but we'll also have each of the components to have shape given by the observed index, which was 21. So we can also sample from this now that we don't have the discrete variable that we have to infer from. We can use nuts throughout the entire process, so convergence should be easier to attain. We can also plot the model's graph, and we can see now that we don't have the label distribution, and this looks really much, almost exactly the same as the linear regression. The only difference now is that the slope has dimension 2. And we can plot our predictions on the training dataset, and everything works fine. But what happens now with the test data? With the test data, once we try to do the sample, we again see something that informs us that we can't broadcast something that has shape 10 against something that has shape 21. So 10,2 against 21,2. So again, something that has to do with a mismatch between what was defined at build time based on the training data set with something that was changed by set data for our runtime. So again, why? If we look at the graph now, we have no idea why, and that's key. There's no apparent reason from this graph of the model, and those are the key things that you say, okay, what's going on? And the thing is that in this mixture distribution, the components of the mixture, the components of the normal mixture, the distribution of the components, is not included inside of this graph, and the shape of these mixture components doesn't change when you do the set data, and that mixture distribution, or the components of the mixture distribution, will always be frozen to have, or to assume, two components, 21 entries, and that's set upon distribution construction. So what do we do? And there doesn't seem to be much of a way out of this with the normal workflow, so we have to try to think outside of the box. And outside of the box means using PyMC3 in a way that it wasn't actually designed to be used. So we have to use it in a functional way. We have to make something called a factory function that constructs new models on request for new data. So this is a way in which PyMC4 was going to be used and defined. And it's not the current workflow for PyMC3. So what we do is we basically have a function, we pass it in the regressor data and the observed data as arguments to this function, and they spit out our model instance that's built on demand. And the good thing about this is that as it's being built on demand, it won't have any of the problems of the shape, because it will always be defined on build time with the correct shape. And we can also define, and we can also change any aspect of the model. So these are the two pros that this thing has. But the cons are, we have to do a lot of manual tuning. We have to do repeated model compilation. We have to potentially remove elements from the trace to do posterior predictive checks. And we have the added overhead for plotting. And basically, none of this should be necessary. So in the future, PyMC3 will strive to work in a different way, in which we can avoid all of the problems of these shape things for posterior predictive, sticking just to the way everything was working now, using Theano and symbolical operations. So this is an example of what I mean by a factory function for the last model that I introduced, the scalar mixture. And so basically it's exactly the same definition as before. We have the same model context. We have the same definition for the regressor encapsulated in data. We have the same definition of the slope, the intercept, the observed output, and we're returning the model at the end. And we can do inference here. And what's important here is that we're calling the function on the coordinates, the training data, and the training observed data. And this is giving us the training model context. So we're doing inference on a model that was defined for the training data. So we get a trace, we get the posterior predictive, we get the prior, everything works fine. We can plot the predictions on the training data, everything works fine, but that's not surprising. What do we do, or how do we proceed now to do posterior predictive sampling on the test data, in which none of this worked before? So now we're calling the same factory function, but now providing it with a different coordinate because we've changed the observation index. We're calling it also, well, now with the same test, with the different test regressors and the different test observations. And we call now the sample posterior predictive. And you can see now that everything worked. We actually get samples from the posterior predictive distribution, and they do make sense with what we actually observe for things. So we're using the trace that we've learned and we've sampled in one model that was defined separately on a different model, in a different model instance, I mean. So it's exactly the same structure of the model, but now it's a different instance in Python. And we use this new model to make the predictions. And this works. But factory functions aren't a silver bullet. And why? The thing is that once you draw samples from the posterior for some parameters, these samples will have the shape that's defined by that parameter. So when we go to the latent label model that we saw before, we have the label categorical distribution that has this observation index. And this label random variable is a free random variable, and it will be included inside of the trace once we do sample, PM sample. So if you can try to guess where I'm going to. So you can draw samples from the prior, you can do inference, you can draw samples from the posterior predictive for the training data set, and everything works fine. But once you try to do predictions on the test set, things break out, things break down. So why do they break down now, if everything was defined perfectly? The thing is that once you input the trace, this trace contains values for the label random variable that have the shape that was incorrect, that was defined upon the training data set. And you can test that. You can look at the entries for label and look at the last entry for the shape, and it has shape 21. So the shape and the values of the inferred labels are determined by the training data. And to make new predictions, you have to do something about that. And that makes sense, actually, because if you imagine what the label represents, it represents that each of the observations of your training data set, you didn't know to which class or to which component they belong to. And once you get new data for the test dataset, you won't know either. But this time you won't have any observations to actually infer the values of the components for each of the new dataset. So you should actually just drop all of the inferred labels that you inferred for the training dataset to make predictions on the new data. And the way in which you do this is also manually tuned. So it's uncomfortable, it's a lot of overhead. It shouldn't be like this, and we'll try to make this better, a better user experience. But once you remove the label from the trace, posterior predictive sampling works. So why is sampling from the posterior predictive distribution so hard? And I think this has to do with the history of PyMC3 that was designed with a focus on posterior inference. So learning from observations, learning the posterior of unobserved parameters. And Theano was used only to build the models log P, and so our distributions mix Theano-symbolic tensors with things that are defined outside of the Theano computational graph. And in particular, the thing that's the most bizarre mixture is in the method that's called distribution random, because prior and posterior predictive rely on that. So the random method does a sort of a ping pong between compiling Theano symbolical tensors into functions, computing them at some runtime, and then returning the results for SciPy to generate random variables, and then doing a ping pong again, compiling, and all of these recurrence relations comes from this basic structure that all of our distributions follow. Each of the random methods basically first draw parameter values from the distribution parameters. These draw values will compile any functional, any symbolical Theano tensor into an actual function that will be called using the inputs that it has from whatever, and that generates a NumPy array of data, and that data is passed on to SciPy to generate the random variables, and then these results are passed on to whatever. And so this could be a random call that's nested inside another draw values statement, because you could have distribution parameters that are actually random variables themselves. This happens all the time in prior predictive sampling. And so the problem is that Theano has the symbolical tensors that have their shape sometimes completely unknown at build time, and you can only have them at runtime, and the runtime isn't available to the distribution once we build it, so we can only see the shape at runtime, and that's a problem to us. Our distributions cannot adapt their shape at runtime, and our distributions cannot infer their shape based on symbolical tensors from Theano at build time, because sometimes those don't even actually have a shape. So what can we do to make this better? What can we do, or as a community, to help? So the alternative now clearly is to go fully symbolic. So we will change the distributions of PyMC free to work with the random variable operator. So there's actually the symbolic PyMC repo at GitHub that you can all check out, and any contribution that tries to port all of the random variable operator from symbolic PyMC into PyMC free is incredibly welcome, and that's the clear road ahead of us. And so with that, I thank you very much for your attention, and hope you enjoyed PyMCCon.